Now mechanical energy is actually the sum of kinetic and potential energy. So till now we have learned the formula for potential energy. This is the energy which is possessed by a body by virtue of its position, that is mgh, right? For example, a body which is kept at height h of mass m, the formula would be mgh. Secondly, the kinetic energy is the energy possessed by a body by virtue of its motion. That means the body is moving with some velocity. So if a body of mass m is moving with velocity v, the kinetic energy is given by half mv square. So what is potential energy? Potential energy is the sum of kinetic energy and potential energy. This is called, I think I said something else, I used some other energy. Mechanical energy is the sum of potential energy and kinetic energy. So this is mechanical energy, alright. So we have to learn about, there is a law of conservation of energy that states that, the law of conservation of energy states that energy can either be created or destroyed, can only be transformed from one form to another. That is right. But there is a law of conservation of mechanical energy which states that total mechanical energy of a system of anything remains constant. It does not change. So what we are going to do right now, we are going to prove this law that mechanical energy remains conserved, or we are going to talk about conservation of mechanical energy. Alright. That was in that the other statement was in some other words. Okay. So how we are going to do it? We are going to suppose a body of mass m which is at height h from the ground, alright, and it is free to fall. That is it. Let's say the height right now is h and it is falling freely. Or we have just dropped a body from h height. Okay, so initial velocity would be 0. This is something we already know. Now we are going to find its energy at 3 different positions. One is at the beginning of the motion, second somewhere in between, not precisely in midway of the height. The second position could be anywhere, let us say here, and third position when the object hits the ground. Okay, so this is one position, this is another position, and this is the final position. For at position number 1, mechanical energy is potential energy plus kinetic energy. Therefore, what is potential energy at h height? The body is at height h, so it is having this energy only in the form of potential. So this will be mgh, but body is initially just dropped. That means its initial velocity is 0. So kinetic energy is half m0 square, so it is going to be 0. So total energy at position 1 is mgh. I'll write like this. Total energy at position 1 is mgh. Let's talk about position number 2. No, we'll do the position number 2 later on. First, let's talk about position number 3. Total energy at position number 3 is given by potential energy plus kinetic energy, right? So potential energy at ground where height is 0 would be 0 because there is no height involved, mg into 0, so this one is 0 plus kinetic energy. Now the body must have attained some velocity while covering this h height, so it must be having some sort of velocity. So velocity is non-zero term, it is a positive quantity, so it must be having some kinetic energy, that is given by half m v square. Let's find out the value of v square in rough. From here to here, body has covered a distance of h. Acceleration due to gravity is positive g because the body is falling vertically downwards. So we are going to use third equation of motion, which is v square minus u square is equal to 2as. But instead of as, the a is acceleration due to gravity and s is the displacement covered, which is h. U, which is initially 0, so we are left with v square is equal to 2gh. Putting this value of v square here, I'll get half m into 2gh. So 2 gets cancelled out and I am left with mgh again. So you can see the total energy at position 3 also is mgh, right? Okay, so let's talk about somewhere in between position number 2. Okay, let's say the object is height x, or we can also say that object has covered, either ways it is right. If I am taking this as x, so this would be h minus x, or if I am taking this height would be h minus x, right, this distance, or if I am taking this to be x, this would be h minus x, right? Either ways I'll get the same answer. So let's talk about position number 2. At here, total energy at position number 2 would be potential energy plus kinetic energy. Now, what is potential energy at this height? The height is h minus x. So potential energy is mg h minus x, right? This is the height from which above the ground the object is placed right now. Plus kinetic energy, that is half m v square. Now I don't know anything about v square this time. V dash, okay, I have taken v there, so I'll consider this as v dash square, so it won't create any confusion. Moreover, v dash square is the velocity this body has attained after covering this much distance, that is after covering x distance. So this becomes mg h minus x plus, for v dash square I'll be substituting something else. So from this point to this point, let's calculate using the same equation of motion, which is third. V dash square minus u square is equal to 2as. So I'm changing the values. First of all, u square is equal to 0, v dash square, u square is equal to 0 because object was initially at rest. 2, a is acceleration due to gravity, and s is the displacement or distance downwards direction, which is x, right? So v dash square is 2gx. Put this value of v dash square here, I'll get half m into 2gx. So this 2 gets cancelled out and I am left with mgx. So here mg h minus x plus mgx, right? Now open this bracket, I'll be getting mgh minus mgx plus mgx, that is this term. So these two terms gets cancelled out and I am left with mgh only. So again, total energy at position number 3, which is this mgh, is same what we got for the position number 1 and 3. So by this derivation we prove that when a body is in different situation altogether but total energy remains same, that proves a law of conservation of mechanical energy.